Yes, sir, we can start.
Yeah, okay. So now we are going to do 1 hour lecture, get to know about response surface methodology. Uh, Essentially, let us say that you are guiding some students and they are doing experiments. You don't want to ask them to do experiments covering a very wide range of variables. For example, you don't want to go from temperature of 30 degrees centigrade to 1000 degrees centigrade in one jump. So you probably will tell the student, okay, you start with 30 degrees, go up to 100 degrees in your first set. Make sure the setup is not blowing up. It is a safe way of doing the experiment. So do it over a narrow range of variables. Pressure, don't vary too much. Vary only over a moderate range. And then do the experiments. And after the student methodologically carries out the experiments and there is no explosion or any incident, we have certain results with us, but the guide will say, okay, the results are looking nice, but probably you can do better. And what direction to go? Okay, if you are having two variables, temperature and pressure, let us say that they are representing the x and y axis. What is the direction for finding the new set of temperature and pressure? Should we go at 45 degrees or keep temperature fixed at some value and then increase the pressure, or keep the pressure fixed at one value and vary the temperature? Even with two variables, we are having plenty of options. And imagine there are 4 or 5 variables entering the fray, and we have 5 variables affecting the response. In which direction we should go and do our experiments so that there is an increase in yield, okay, or increase in efficiency or output, and so on. Whatever is our desirable outcome, we are able to achieve. What should be the direction in which we should proceed? Again, we cannot be wandering around in an n-dimensional experimental space, going here and there and getting lost somewhere. So design of experiments and response surface methodology gives a very elegant way of handling this problem. So you can see that, let us say that you are starting at some point here, then you want to quickly go in this direction so that you hit the global optimum. Okay, you can see that the region is pretty flat here, but when you go further into the domain, from a flat plane, it is starting to become mountainous. Okay, and fortunately here you are able to achieve the maximum. So this is our target, and most likely we are somewhere here. So how to advance from this point to this point in the quickest way possible? Again, this is a biotechnology experiment, butanol and CTAB. CTAB probably is a surfactant, and then they are focusing on recovery. And neither at highest value of CTAB or the highest or lowest value of butanol, you are able to get highest recovery. Neither are you getting the highest recovery at the maximum value of CTAB and maximum value of butanol. We normally think when you increase both the reactants or both the ingredients to the maximum value, we will get the maximum response. Okay, it does not happen like that. Okay, I remember reading an example on design of experiments where a teacher, he wanted to do experiments in the class. He put vinegar and salt in chips and asked the students to taste the chips. Any problem? Okay, so he put either vinegar or salt in the chips, and then he asked the students to taste the chips and tell which is better. Students were very happy. For a change, we are not getting homework, but we are getting chips. And so they all responded, and they said that putting vinegar in chips had a better response than putting salt in chips. Then one student said, why not put both vinegar and salt in chips? Maybe the taste will be better or the best when you have both vinegar and salt. And so the teacher said, oh, that's a fantastic idea. And then he carried it out. And surprisingly, at some intermediate value of vinegar and chips, vinegar and salt concentration, the chips tasted the best. Okay, so what we understand is not how to make chips, but the important concepts behind it. When you add only salt, you get a particular response. When you add vinegar, you get a particular response. But when you add both, you get a synergetic response, and the outcome is much more than what you expected from a linear combination of vinegar and salt. Okay, the response is much higher than a linear combination of this. Suppose you are having two students who are getting 80 and 90 in the subjects, and their parents decide if they are getting 80 and 90, how much they will get if they are studying together. Maybe they'll get 100. So let us put both of them together and let us see whether their performance is improving. And if, as their parents expected, the two students are getting 95 marks, then there is a improvement. But what is happening is, if the marks suddenly fall to 40 and 45, then what is happening is the two students, instead of studying, are probably gossiping about IPL, cricket and all that, and so their performance has declined. So when two variables are there, they can either be independent, they can be interacting, and if they interact, they can interact in a positive way or a synergetic interaction, or they can interact in a negative way or a antagonistic interaction. So when you have these three possibilities, the response is what you expect from a linear combination of the two variables. That would be a independent interaction. There is no interaction. But if you have a synergetic interaction, the response is much greater than what you believe. And when you have a antagonistic interaction, the response is much lower than what you expect. So obviously, rather than increasing the butanol to the full value or CTAP to the full value, at some intermediate point, you are having a maximum in the response. So this is very important for you to recognize that interactions between the variables can play a very important role in determining the optimum conditions. This is another peculiar response surface where the optimum is not very well established, and you can see that it is kind of flat surface, and the contour plots, earlier the contour plots were well defined, they were circles, but now the contour plots are becoming more like ellipses. Okay, along one direction there is not much change in the process response. Along this direction there is not too much change in the process response, and the response contours are getting elongated. And now this is a much more complex surface where you have both maxima and minima. I don't want our students to do experiments in such a way. If the ultimate aim is to maximize the response, they start from some point here, and instead of going in this direction, they go in this direction and get the minimum value in the response. Okay, so instead of maximization, they have done the minimization. Okay, and this region is also very complex, and very frequently your optimizer which you are using, instead of reaching the global optimum here, may go and hit a local optimum somewhere here, or it may hit a local optimum somewhere here. So we may be thinking that is the best condition. You can see a contour plot with the circular elliptical contour plots, and you may hit a local optimum here rather than a global optimum corresponding to that point here. So this is a very complex problem, and people are now slowly waking to the fact that whatever simple optimization techniques they have carried out may not have detected the global optimum, especially when the number of variables were more than 4, then possibilities of local optima abound. And so they have started looking into soft computational techniques rather than conventional optimization algorithms like Nelder-Mead or Simplex or Levenberg-Marquardt. They have gone beyond these simple algorithms. They have gone into soft computational techniques like ant colony optimization algorithm, genetic algorithm, simulated annealing, social spider algorithm, particle swarm optimization, to name a few. I'm not sure whether I left out any more optimization algorithms, but these are soft computational algorithms, and they are mimicking foraging species which are hunting for food, and they are found to detect the global optima without too much of an effort when compared to Levenberg-Markov or simplex algorithms, which keep shrinking in size near the global optimum and never reaches the optimum. So this is very fascinating field, and people are either going for response surface methodology or artificial neural network to model the response, as I told in the first session. Yeah, I was invited to a textile department to talk about design of experiments. I had next to nothing knowledge on textiles, even though the department was adjacent building to a chemical engineering department when I was doing my BTech. So I thought, what is there going to be in textiles where they'll be employing design of experiments? What are they really interested in? Why should textiles have something to do with design of experiments and response surface methodology? So I just did a literature search, and then I found that there were a lot of examples in textiles where the design of experiments were carried out. Processing of textile, modification of existing textile, and treatment of textile wastewater. So you can see some of the responses which they had predicted using the design of experiments. They were trying to optimize the processing parameters on needleless electrospinning. Okay, maybe the textile practitioner will be understanding more of these terminologies, but they were using it in the textile manufacture. And then you can see that optimization of wool slenderizing along with in situ synthesis of silver nanoparticles using a Box-Benken design. And then dyeing of modified cotton fiber with natural dye, optimization of dyeing parameters using response surface methodology. So no matter what application in engineering you take, nowadays the trend is to go for design of experiments. Actually, let me put it like this. Design of experiments is not a magic wand which will get your paper accepted by the editor. Okay, but when you are arguing your case in terms of design of experiments and response surface methodology, nobody can contradict or counter your claims, because not only you are giving the inference from your design of experiment study, but you are also giving the probability of the error associated with that particular decision. Okay, if somebody is not happy with p-value of 0.05, let them set a p-value of 0.1 or p-value of 0.01, and then he can make a conclusion with that associated p-value, with that particular error value. So your judgment and your conclusions and your inferences cannot be questioned, and that is what I always tell my students. Don't expect that your papers will get accepted just because you are doing design of experiments, but the benefits are you are going to do less number of experiments, you are able to analyze the experiments better and more economically, more efficiently with less time, and you will be finishing all your experiments in 1/3 of the time which you will take if you are doing a conventional route. And not only you can do that, but you can also do optimization and get the optimum settings for your experimental program. Okay, so these are some of the contour plots from that paper, which was looking at modified cotton fiber with natural dyes. And this is textile waste using experimental design. So many journals, many papers, and response surfaces. So whenever you take any application, you will find people are doing experiments with design of experiments these days. Okay, so now let us take a very simple case where Z is the response and X1 and X2 are the parameters or the independent variables. Okay, X2 can be pressure and X1 can be temperature. So when you plot the contour plot, you are going to have these lines. So what it essentially tells me is, and these are straight lines, and each of the line represents a constant value of Z. For example, this dark line is Z is equal to 2, the blue line is Z is equal to 4, and then Z is equal to 6 for the red line, and for the last purple line Z is equal to 8. So what you do is, for example, Z is equal to 6, you put the value of z is equal to 6, 6 by 3 is 2. So what should be the combination of x2 and x1 such that you get a value of z of 6? So this is a locus of points of x1 and x2 such that the z value is equal to 6. Similarly, this is a locus of points of x1 and x2 where the z value is 4 and so on. Okay, suppose I want to maximize the value of z. So what I can do is I can fix x1 and at a value of let us say 5, and then what I'll do is I'll vary x2. I'll obviously you can see that it is decreasing. Okay, if I'm going in this direction, it is decreasing. So I'll probably be going in this direction. At a fixed value of x1, I'll be decreasing x2, and then the z values will start to increase. Okay, and so I'm going to come down like this, and then I'll hit this -3 for x2 for a given value of 5. And then what I will do is I'll fix the value of x2 at -3, and then I'll start decreasing the value of x1 so that I will reach this particular point, which is the minimum value, for my response. Okay, this is another example. You can see that the response is now increasing with z is equal to 35. So let us say that I am fixing at 5, then I'll be increasing x2 along this direction. I'll hit a value of 12, not a value of 12 for x2. Then I'll keep the value of x2 at 12, and then I'll start increasing in this direction, and this corner will give me the optimum value. So I'm doing one variable at a time response optimization. I'm fixing one variable, varying the other variable, finding the optimum response. For that particular value, I'm fixing at that value, then varying the second variable, and I'm finding what is the optimum response. Okay, imagine doing this for 5 variables. You probably can do. You fix all the 4 variables at a constant value, average value, then you vary x1, get the optimum, then you keep x1 at the average value, x2 you vary, keeping x3, x4, x5 at average values, and then you find the optimum. You keep doing sequentially, systematically. You are thinking that you are going to end up with the global optimum, but that is not true. Let us take this example. You can see that here, if you are keeping a temperature constant at not temperature constant, sorry, what are you keeping constant here? Let us say that you are keeping pressure. This is temperature and this is time. Okay, you are keeping time constant at some value of, let us say, 1.75 hours, and I am finding that I am varying the temperature. I'm keeping temperature at 155 degrees centigrade. I'm varying the time from 0.5 hours to 2.5 hours, and then I find this is the maximum value. Then at this maximum value of temperature of 155 degrees, I'm varying the time from 140. I'm keeping the time at 1.75 hours. Let me go like this. So I'm keeping temperature at 155 degrees centigrade, varying the time at 1.6 or 1.7 hours. I get the optimum value. At that optimum value of 1.7 hours, I am varying the temperature from 140 to 180, and I'm getting some value here. Okay, so this is the optimum value as far as this one step at this time is concerned. Or what could have happened is the temperature might have been fixed at 150 degrees centigrade, and the person could have gone in this direction, found the optimum value, and then gone in this direction and found this as the optimum value. So this is one variable at a time strategy, but because of curvature in the design, your one variable at a time methodology is not working, and the true optimum is lying somewhere else. So what has happened is the strategy one variable at a time was not able to pick up the true global optimum. So this is the response where they are varying the time. They are varying the time from 0.5 to 2.5 at a given value of temperature. And so they find the optimum time as 1.7 hours. And at 1.7 hours, they are varying the temperature. Okay, at 1.7 hours, they are varying the temperature. And they find an optimum yield of about 80% at 155 degrees Fahrenheit. 155 degree Fahrenheit and 1.7 hours are stated to be the optimum. And you are saying that by doing optimization, I was able to increase the yield to about 75%. But the true optimum is 95% or even higher. Okay, by missing out on the true optimum conditions, the maximum yield of 95% and above was missed by the experimenter, and he had to settle for only 70%. Imagine the cost benefits in an industry from 75% to 95%. Okay, you are going to gain a profit of millions of dollars by going from a yield of 75% to 95%. Many of my students who do my course, or they do the course after, they go for an internship, an industrial internship, and in that industrial internship, they do response surface methodology to optimize their processes. So they get excited and then they come and do the course, or they say, your course was very useful because I was able to participate in the response surface methodology design and I was able to give some helpful contribution to the optimization. Okay. So this is the basic regression model we start with, and this is the response beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon. This is the true model. This is the random error term, and when we are predicting the response, we are having y hat is equal to beta hat naught plus sigma beta hat I xi. So we are estimating the parameters of beta hat naught and beta hat I. Using the available experimental data generated in our lab. Okay, and these beta hat naught and beta hat I may not be equal to beta naught and beta 1 and beta 2. These are the absolute true values of the parameters, and they are unfortunately unknown. So we are going to do best with whatever we estimate, beta hat naught and beta hat I. Okay, let's move forward. And I think what we'll do is I'll just give an example, right? So what we do here is, let us say our response is like this, and fortunately in this case there is no interaction between x1 and x2, so you don't have any curved responses here. And what you do is you do your design of experiment in this box, and once you have identified the responses from the center value of the design, you go in the direction of steepest ascent, path of steepest ascent. And the path of steepest ascent is one which is normal to the lines. In this case, lines, it is normal to that. So you go in this direction. This is the direction which is going to give you the maximum increment in your response. Okay. So you have fitted a linear model, y hat is equal to beta hat naught plus beta hat I xi. You have fitted a linear model applicable for this region. Okay, you have done experiments in this box. And what you are doing now is you are extrapolating, you are assuming that the model which you have developed is also applicable outside the box. That is something which you cannot do. Your model, whatever correlation or empirical equation you are developing, is only applicable for the region or the range of experimental data conditions in which it was developed. You cannot extrapolate it because you did not do experiments beyond that particular region. So assume that, so what is going to happen is, right now, as I told you in our diagram, you're walking on a plane, but pretty soon, the terrain on which you are walking can become extremely steep and highly mountainous with a lot of peaks, valleys, and all that. So assuming that you are having a plane surface and you go without making proper precautions or arrangements for climbing the peaks, scaling the peaks, you're not going to be able to climb the top. Okay, so this is the direction you are proceeding. This is an initial direction. So what we can do is we can proceed along this direction. After we reach a particular point, we pause, we reassess our situation, and again we do a design of experiment around this region to see whether the terrain is now starting to become curved. If not outright mountainous with peaks and valleys, we want to check whether the terrain is becoming curved or slopey or inclined. So that's what we want to see. And after we reassess, again, then from that point, we go in the direction of steepest ascent, and then we go to a new point and see whether we are seeing mountains, peaks, valleys, and saddle points. Okay, that is our strategy. Okay, so I set up this example from Montgomery 2009. A chemical engineer is interested in determining the operating conditions that maximize the yield of the process. I think I will skip all the story. Anyway, let us go through the story anyway. Two variables are time and temperature. The engineer is currently operating at 155 degrees Fahrenheit and 35 minutes reaction time, and the reaction yield is only 40%. Okay, nobody is going to be happy with only 40% yield. So we do a preliminary screening experiment, and we set our range of temperature to be 150 to 160 degrees Fahrenheit and time from 30 to 40 minutes. Okay, so this is the data. So rather than writing 30 and 150, 40 and 150 and all that, I want to tell a very important thing. When you are writing a model, beta hat naught plus beta 1 x1 plus beta 2 x2, we sometimes can jump to conclusions. If beta 1 is 100 and beta 2 is 2, then we'll think that 100, the beta 1 x1, the beta 1 is 100, beta 2 x2, beta 2 is only 2, beta 1 is more influential, or x1 is more influential than x2. Okay, that is what we will conclude, because the coefficient of x1 is 100, coefficient of x2 is only 2, so x1 is more influential on the response. Okay, and then you may even say, okay, I leave out x2 because the coefficient of x2 is only 2, so I leave out x2 and I'll assume that only x1 is influencing the process. Why is this wrong? Can somebody give an answer? Okay, very simple answer is, let us take the example, x1 is time, x2 is temperature. Let me just take it. x1 is time, x2 is temperature. You can see that there is about an order of magnitude difference between x1 and x2, or maybe about 5 times. Okay, 4 to 5 times a difference between x1 and x2. So if I'm using x1 as, which is, yeah, x1 is time. Time is a lower value, and temperature is the x2 value, which is our higher, 5 times higher than time. Then the coefficients beta 1 hat and beta 2 hat will reflect the units. Okay, so if, for example, temperature is having time is having more influence, or temperature is having more influence, we cannot really say by looking at the coefficients, because x1 is having different units, x2 is having different units, x1 is in the order of 30 or so, x2 is in the order of 150. So in such a case, when we are having different units, for example, what I can do is instead of time in minutes, I can put time in milliseconds. Okay, then I'll have x1 in the order of thousands and much 2 orders of magnitude when compared to x2. So all this confusion will come, and we are not able to decide whether beta 1 is, compare beta 1 and beta 2. the coefficients of x1 and x2. So what we should do is code the variables and make them fall in the same range between -1 and 1 for both x1 and x2. Okay, so we have to code the variables and bring it to the same basis. And once you do that, then you can compare beta 1 and beta 2, beta hat 1 and beta hat 2. After coding the variables, if you find beta hat 1 is 10 times higher than beta hat 2, then you can say that, okay, x1 is having more influence on the process because the coefficient for the coded x1 is 10 times higher than the coefficient for coded x2. But without coding, if you're trying to make this generalization and conclusion, then it may be wrong. So as you can see, I'm just coding it between epsilon 1, the value minus 35, the average of 30 and 40, my lower value and the highest value. So epsilon 1 minus 35 divided by 5, x2, epsilon 2 minus 155. 155 is the average of 150 and 160. My lowermost temperature and higher uppermost temperature, 155, epsilon 2 minus 155 divided by 5. And then we get x1, x2 falling between -1 and +1. And I'm also doing experiments at the average value of x1 and x2, 0, 0 and all that. You have the response here. So you have the responses here, 39.3, 40, 40.6. These are repeats. As I told you, every experiment should have repeats in them so that you have an idea about the experimental random error. So this is 40.3, these are the values, and these are the other responses. So we calculate the error variance and it comes to 0.043. So after you fit a model, a linear regression model, you can fit y hat predicted will be 40.44 plus 0.775 x1 plus 0.325 x2. So you can see that now the time is having more effect than the temperature. X2 was temperature, I guess. Yeah, x1 was time. So x1 is having more effect because these are all in coded form. And x1 is time is having more effect than temperature. Okay, let us move forward. So before we are in a hurry to climb the ladder for steepest ascent, so we have fitted the first order, we have fitted a model here, a linear model, linear in x1 and x2, a first order model because we are not having a higher order terms. So we want to go in the direction of steepest ascent. But our model may not be satisfactory. We might have neglected curvature in the response. The responses, instead of being straight lines, could have been curved lines. So a model is what you make out to be. But our thing is whether it represents reality. So you are fitting a linear model to a curved data, okay, data trend. So if the contour plots were rather curved, then there is a curvature. So you have to account for the curvature, okay. And that is where the center points play a very important role. Not only the center points are essential for you to find the pure error or the random effect, random error. Remember the motor problem, the engines you did for each brand of petrol, you took 5 engines. So you did for each brand of petrol 5 repeats. Similarly, the average settings of your design at average values of time and temperature, you're doing repeats in order to get an idea about the pure error or the random error. All right. And so we are not very sure whether our response surface is having curvature or it is a flat plane. So how do we test it? The center points help us in that aspect also. Let us look at a very geometrical, let us now look at a geometrical thing. So right now your center points are here and these are 4 corners of your rectangle which you set your experiment. So what we want to know is if there is curvature in this domain, whether this surface is plane or having curvature, we can easily find out. What we can do is we can compare the average value of the center points with the average value of the corner points. And if the average value of the corner points and the average value of the center points are more or less equal, then we can say that there is no curvature in the response surface. But if the corner point average is much lower than the center point average, then obviously there is the center points are lying at a higher position when compared to the corner points. So when that is happening, in this case, the responses are not having that much of curvature. But suppose the y bar f, this is what you would expect when you have a planar surface. But if the surface is curved like an inverted saucer or an inverted cup, then your center points may be sitting somewhere. Let us say that at this point, average of the center points may be sitting somewhere here, and these corner points may be having an average of some value here. Okay, y bar f is this value, y bar f, this is y bar c, center points. We want to see whether y bar c is very close to y bar f or this is very far off from y bar f, and then we can detect curvature in the plane. So that's what we are going to do, and okay. So we do a regression test, and what we do here is, I'm really cutting short on certain things because of lack of time, but I hope you are able to follow. This is our original linear model. I want to see whether curvature is there, not just slope. Okay, whether you are having a slope or an inclined slope of variable slope, okay, or some twists and turns in the surface, not really peaks and valleys, but kind of twists and turns in the response surface. To account for it, you are adding the interaction term beta hat 1 to x1, x2. And since all the x1, x2 are coded, okay, you can see that y hat is coming out to be 0.775 x1, 0.325 x2. What was the value we got earlier? 0.775 x1, 0.325 x2. Okay, so we are getting 0.775 x1 and 0.325 x2 minus 0.025 x1, x2. Okay, so by looking at the coefficients of the models, it does appear that the interaction between x1 and x2, which can cause the curvature in the response, is negligible. One more thing you will ask, if you are very alert, what you will ask is, that's why I went back and checked. When you are ignoring the x1, x2, you are not putting x1 into x2, you are getting 0.775, 40.44 plus 0.775 x1 plus 0.325 x2 you are getting. But when I am adding one more term to the model, okay, x1, x2, 0.025 x1, x2, again you are getting the same intercept, 40.44, 0.775, 0.325. When you are adding more model terms, I would have expected these values to change. Okay, what is the significance of 40.44? 40.44 is the average value of the response. Okay, when x1 is 0, when x1 is not having any effect, x2 is not having any effect, x1, x2 is not having any effect, the response is nothing but the average value. So the deviation from the average value or this deviation from the average value are brought out by these terms. So 40.44 is the average of all your responses. Now imagine, that's what I told you about Fisher. When he visualized, he said that the contribution of sum of squares from x1, contribution of sum of squares from x2 are independent of the contributions from x1, x2. So all these terms are independent. Whether you fit only x2, if I fit only x2 and remove x1 and ignore x1 and x1, x2, I'll get only 0.325 x2. If I had ignored x2 and 0.25 x1 and x1, x2 also I had ignored, I will still get in my regression model 0.775 x1. Why is this? Because I'm doing a factorial design, and this factorial design is called as an orthogonal design. You add all the elements, -1, -1, -2, +2, 0. Here also you add, it will become 0. When you multiply 1, -1, -1, 1. Again 2 minus 2, 0. So it's an orthogonal design, and irrespective of how you add or remove terms from your model, you're going to get the same coefficients. That is the big advantage of orthogonal designs. but this is not true for non-orthogonal designs like conventional regression. And when you do that, when you leave out x1 and you model only in terms of x2, the parameter you get will be the coefficient you will get for x2 may be different when you compare from the case where you consider both x1 and x2. Okay, so these are some intricate aspects of regression which you should be aware of. So this is a design Minitab output. You can see the p-value. What was our null hypothesis? Our null hypothesis was the coefficient of time was 0, the coefficient for temperature was 0, coefficient for time into temperature was 0. That was our initial hypothesis. The model is useless. It is not going to be able to explain the variability in the data. Look at the p-value for time, 0.002. Look at the p-value for temperature, 0.035. Since the p-values are very small, the probability of wrongly concluding that the parameters are significant is very, very less. Okay, so 0.002, 0.035. But when you look at the interaction, the p-value is 0.821, much greater than 0.05. So we can reject, we have to accept the null hypothesis that the parameter or the coefficient for time and temperature is 0. So since the p-value is, the probability of making a type 1 error is very high, the probability of wrongly concluding that this factor is significant is very high. So we accept the null hypothesis, saying that time and temperature is not having an effect on the process. So if the p-value is very small, reject the null hypothesis. If the p-value is very high, accept the null hypothesis. If the value, the boundary or margin is 0.05. And this is the sum of squares. Whether you do it sequentially or do it term-wise, the sum of squares is the same. That is another take-home message from here. Okay, so we have concluded like this, and now how much time do we have? Because I don't want to overstep the time. So I think we have about 20 minutes. We said we'll stop at 12:15. Yeah, I think I can do it. So we do some statistical tests. We do some statistical tests and conclude whether curvature is significant or not. Okay, now let us move further away from our current model. We'll move further and further away from, we'll venture further into the wilderness. And when we venture further into the wilderness, we are going to see some inclines, some curvatures and things like that. And then suddenly it is going to start becoming mountainous and hilly and with peaks and valleys where we have to tread carefully. So what we then do is we account for such a case by looking at not only main effects x1, x2, not only curvature effects beta hat 1, 2, x1, x2, but we also look at beta hat 1, 1, x1 squared plus beta 2 hat x2 squared. Okay, so y is equal to mx squared is an equation of a parabola where you have a steep increase. When you have a two-dimensional case involving x1 squared, x2 squared and all that, you get a peak in the peak value at some combination of x1 and x2 because it is a combined response. So you are going to have this quadratic effect representing the peaks of the experimental design surface. This represents the curvature and this represents the planar region. So geometrically, like Fisher, we are able to visualize our response surface as being composed of a contribution from a planar region, contribution from a curvature, and contribution by peaks and valleys. Okay, I think I'll skip this because this will involve a bit of statistics concepts, t distribution, which some of you may not recollect, even if you have studied a long time back. But I think we'll go forward. Okay, So I think we are going in the direction of steepest ascent. So you have this simple model, the preliminary model. We write x2 in terms of x1 and y, and then we know the slope of this equation is minus 2.38461. So that normal to this slope will be m1, m2 will be equal to minus 1. So the direction of the normal to the slope is m2 is equal to minus 1 by minus 2.3846, 0.4194. So this is what we are going to get. This is the direction of the normal slope. That means if you change x1 by 1 unit, x2 will be changed by 0.4194 units. Okay, so this is where you are starting, and then this is where you are going. And the direction should be, if I change x1 by 1 unit, I should change x2 by 0.5 units approximately. So this is 1, this is 0.5. So this would be my steepest ascent direction. Okay, so if I take a unit step for 1 along the x1 direction, and we take a 0.4194 units along the x2 direction. So a step of x1 means 5 minutes for time, and a step of 2.097 degree Fahrenheit for temperature. So doing that, okay, we are going from 40 to 45 and 157 to 159, 2 degree centigrade for temperature and 5 minutes for time. We keep increasing our values of the process values, and then they keep increasing, and then the response also keeps increasing. Okay, but you may be asking, are you not contradicting yourself? You are saying that you go in this direction of steepest ascent. You are saying go in this direction of steepest ascent. You only told that the model you have developed, based on which you are calculating the steepest ascent, is based on this thin small region. Okay, but when you venture out of this region, you may not get mountains and valleys, but you may get curvature. So your these response surfaces may be having curves like this. It may be curved, it may not be straight. So how can you go along the direction of steepest ascent? What you can do is, you can again, after going for a certain direction, you can again do your experiments. Here you can find the model. There may be curvature in the model, and then based on the new model, you go in the direction of steepest ascent with respect to that model, and then you go for some more direction. But that is going to be really a tedious process. What Montgomery has said is, okay, this direction may not be truly representative or accurate of the steepest ascent when you step out into the wilderness, but there is not too much deviation between the true steepest ascent and the approximate steepest ascent. So for simplicity, you can still pursue along this particular direction, and that is what the engineer has done. Okay, the chemical engineer who was doing the reaction experiments. So what she does is, she increases the values by 5 degrees for temperature and for time, 2 minutes for time, 5 minutes for time, and 2 degree Fahrenheit for temperature. And the response is increasing from a measly 40%. It can even go up to 80%. And then it starts to decline. So the maximum is somewhere around this region. We are not really sure whether this is the optimum point. 80.3 is the optimum point, because our model and our steepest direction ascent was approximate. So what we do is, around this region, we put a more sophisticated design, and this is sketching the values of the response in yield. So around this region, we will sketch up a new design, and that design is the central composite design. So what you are having is, these are the experimental points. So you put a factorial point, and then you have the center points. Center points are necessary for repeats, random error calculation. You have factorial points. You have on the axis 2 points here, and on the axis 2 points here. So now you set up this design, and this design will be able to help you to not only calculate the main effects, the interaction between the main effects, the interaction between the main factors, but also it will help you to calculate the quadratic terms, the peaks and valleys. Okay, so this design is very popular in literature. It is called as the central composite design. So I think I'll skip a few things and okay, I'll skip all this. You can take a look at it and you get the final expression. So you get the responses at all these corner points, factorial points, center points, axial points. So you get the responses in all these points and you have a mathematical model with you. Now you have to use this mathematical model to do the optimization. So you have a mathematical model, and conventionally this is a quadratic model, and because the order of the model is 2, x1 squared, x2 squared, x1, x2, so the order of the model is 2, and what you have to do is dou y hat by dou x1, dou y hat by dou x2 is equal to 0. Solve the two equations and get the values for x1 optimum, x2 optimum.
Sir?
Yeah.
Actually, I want to ask something here, because I have seen generally this type of model, all the people who are doing means RSM actually. So means generally we have the data. So let's say we have concentration and time, and then means how to get this is means these coefficients. Do we have to do a separate fitting, or we can do in Excel actually? What need to be done actually?
Okay. When you're doing a central composite, when you do a central composite design, you are having a particular model. And how many parameters you are having in a model? Beta naught, let us assume two variables, beta 1, beta 2, that is 3, and beta 1, 2, 4, and then you have beta 1, 1, beta 2, 2 for the quadratic terms, 6 parameters. And for two variables, you have 2 power 2, 4, this thing, plus you are having 2 into 2, 4, 8, and then you have some center points, like say 11. So you have 6 parameters, you have 8 data points. So what you can do is with the coded model, coded factors, you can do a regression analysis and get the values of beta 1 and beta 2, beta 1, 2, and beta 1, 1 and beta 2, 2. So you have to estimate 6 parameters. And for doing this parameter estimation, Excel you can do, but there is something called as the matrix approach to linear regression. You have a matrix approach to linear regression, and when you do matrix approach to linear regression, you have what is called as y hat is equal to x prime into beta hat. Okay, and the beta hat, you create what is called as a x matrix, and beta hat is nothing but x prime x inverse x prime y. So you put all your experimental design points in the form of an x matrix and a y vector of responses. You can estimate all the parameters by simple matrix inversion using MATLAB. You can very easily carry out the regression analysis and get the parameters. So very easily you can estimate the parameters. For simple linear regression models, estimating the parameters using matrix method is very trivial. Is it okay? So probably in Excel, you can do matrix addition, multiplication, taking inverse. There is a YouTube video on how to do these matrix manipulations and net. So you can look at the people who are not aware of that may look at it in the net and see how to do the matrix manipulations, create the X matrices and Y vectors and get the parameters very easily if you don't have access to MATLAB. Okay, so we have to do this, and again I'm going to demonstrate the matrix methodology only here. And so this model can be expressed in a quadratic form. Yeah, I think I have another 5-10 minutes. So you can express this in a quadratic form. Y hat is equal to beta hat naught plus x prime b plus x prime b x. Okay, where the b is a matrix of the coefficients beta 1, beta 1, 1, and so on. So let us take a look at that. This is applicable only for a quadratic model. If you are having a cubic model, for example, then whatever methodology I am going to describe now will not be applicable. But very easily you can do optimization in MATLAB using F-min search algorithm. Okay, so this is the X, which is nothing but X1, X2. So these are your independent variables, temperature, time, and so on. This is the matrix of coefficients. Why you are having beta hat 1, 2 by 2? That is because this is a symmetric matrix. Beta hat 1, 2 is equal to beta hat 2, 1. So when you're doing the matrix multiplication, you will be doing beta hat 1, 2 into x1, x2. You'll also be doing beta hat 2, 1 into x2, x1. So since beta hat 1, 2 and beta hat 2, 1 are the same, in order to do the balance the double multiplication, you divide by 2. But the diagonal terms, you don't have the division by 2. So, and this B is beta hat 1. These are all the cross terms, the quadratic terms, the curvature terms, and these are the main factors: beta hat 1, beta hat 2, so on to beta hat k. So using the matrix matrix manipulation techniques or matrix algebra, we can very easily estimate the parameters. So you have the parameters, you have estimates of all these parameters, not only capital B but also small b, and this is nothing but the average value. Okay, so you do the matrix differentiation, and you will find the stationary point to be minus half into B inverse B. So you can, the response is given by y hat s is equal to beta hat naught plus half into xs prime b. Xs is nothing but the vector of the stationary points which you are finding. These are the roots of your normal equations when you set the derivatives to 0. But only thing is we are doing it in a matrix form. And once you do the matrix linear algebra, you are going to get directly the stationary points minus half B inverse B, and then you are going to get the response as well. Okay, so unfortunately, after trying to do a maximization problem, after doing a lot of experiments, we should not land up with the minimum set of minimum response. Our variables which we have identified, our so-called stationary points, when you substitute in this response equation, we should not get a minimum in the response. It will be total chaos. Okay, so how to find whether the stationary point is corresponding to a maxima, or is it corresponding to a minima, or whether it is corresponding even to an inflection point. Okay, in our conventional calculus, if the second derivative is negative, then our identified solution is a maximum. If the second derivative is positive, the identified solution is a minimum. So like that, how to do it in matrix algebra. So that's what we are going to do now. And so we do what is called as some canonical analysis and some canonical transformation. What we do is we represent the response surface in terms of new coordinates w1 squared, w2 squared, so on to wk squared, w1 squared and w2 squared. But these w1 and w2 are not always x1, x2. These are some different coordinate system. And the advantage of this transform coordinate system is the axis, the x-axis and the y-axis will be aligned along the contour plots. Okay, so rather than having a conventional x and y direction, taking into account the direction of the contour plots, after you make a canonical transformation, you have W1 and W2. These are more aligned along the direction of the face. So anyway, you don't have to worry too much about all these things. And what is lambda 1, lambda 2 and lambda k? These are nothing but the eigenvalues of the B matrix. So this B matrix which we discussed, this B matrix is a symmetric matrix, and the advantage of this is it has a lot of information about the model. So if you find the eigenvalues of the B matrix, if both the eigenvalues are negative, you have hit the maximum. If both the eigenvalues are positive, you have hit the minimum. If one eigenvalue is positive and the other eigenvalue is negative, you have hit a saddle point. Okay, so I know that some of these things you cannot become knowledgeable in a very brief time, but at least now you have seen all these things, and you would have noticed how simple these things are, and I hope you will be able to incorporate them into your uh, research work and inform your students accordingly. And the eigenvalues of our things are both negative, and we get our response surface is having a nice optimum. It looks more like a cake. I know I don't want to make you even more hungry than what you are now, but whenever I see this response surface, it reminds me of a birthday cake. Okay, so you can see that this is the B matrix. This is the small b vector, and the stationary point is minus half B inverse of B. This was having all the coefficients of beta 1 hat, beta 2 hat. These are the coefficients of the quadratic terms and the curvature terms. Let us see the model. Do we have the model somewhere? I thought, okay, we have to go a long way back. So let us take these as model parameters. And yeah, so these are the beta 1, 1, beta 2, 2, and beta 1, 2 by 2, and beta 2, 1 by 2. So you can see that these are identical. And these are the values for the coefficients of the main factors. And you can find the stationary point, and you're getting the stationary point as 0.389 and 0.306. 0.389 and 0.306, somewhere around here, 0.306 and 0.4, somewhere around here, you're having the optimum. And eigenvalues, you know the definition of eigenvalues, and this is the characteristic equation. And B minus lambda I is equal to 0. In MATLAB, you can just simply put eigen EIG of B, you'll get the eigenvalues. And you find that lambda 1 eigenvalue is minus 0.96, and lambda 2 is minus 1.414, which is corresponding to minus root 2. I don't know whether there is any special significance to that eigenvalue, but it is very close to minus root 2. I don't know why. All fascinating. If you look into the mathematical aspects, you'll uncover some or discover some gems. So it is a minimum. So I think this completes my response surface methodology. The main point here is for a quadratic model, you can do this optimization. But when you are having a cubic model, this methodology will not apply, and you have to use a rigorous optimization algorithm. And sometimes these algorithms may pick up some non-optimum values. Maybe I'll show you one particular paper before I sign off. So you can see that rather than using the conventional optimization technique, they have carried out artificial neural network and simulated annealing. And the optimum conditions from the conventional technique was pH of 12.57. And from a simulated annealing optimization technique, the pH value was 10.114. So the conditions of pH are less severe in the global optimum, which is desirable. And time is 20 minutes, whereas the time is 9 minutes, 8 minutes. So again, with less time, you're able to achieve the optimum, which is again a desirable result. And then temperature is 39 degrees centigrade. But simulated annealing is telling that you're able to achieve the temperature at 25 degrees centigrade itself, you're getting the optimum value. So why do you want to heat the material up to 39 degrees centigrade, and it may degrade and you are going to lose energy? So industries will love processes. They don't want heating, because when you go for heating, I was remembering my consultancy with an industry. The moment I said you have to heat it to 190 degrees centigrade in order to get best performance, they said forget it. We don't want to heat it even to 90 degrees centigrade, and you are telling 190 degrees centigrade we don't want to heat. We want, because our energy costs will simply blow up and we need to have a very expensive equipment. They said nothing doing. So 39 degrees and then you are saying 25 degrees. It's a remarkable thing. And initial concentration, it's saying you can only go to 36 milligram per liter, but this one says 64 milligram per liter. So there is a discrepancy between conventional optimization method and the simulated annealing soft computation method. And not only that, the global optima predicted by the simulated annealing method is also telling that the conditions are more friendly. So who would not like it? True optimum, which is also a more friendly optimum. So when you do response surface methodology analysis, there's nothing wrong in the central composite design. But when you are using a cubic model and more higher order models, then you have to be very careful in choosing the optimum, and you have to use a proper algorithm so that you detect the global optimum and not the local optimum. So with that, I will wind up, and I thank you for your attention and interest.
Thank you very much, sir. So, any question from participants? Siddharth Modi wants to ask something.
Sir, I have two questions. One is regarding the assigning weights, and second one is regarding the transformation. Am I audible?
Yes, yes.
Yeah, you're audible.
Yeah. So, sir, if my factors and response, if the relation is in terms of AND and OR gate, so what kind of weights I should assign?
No, I didn't get. You are having a response and you are having factors.
Yeah, the relation is in terms of gate, Boolean gates.
Oh, okay.
So, what
Okay,
kind of
you are,
weights I should?
okay, you are having yeah, you are having discrete variables, right?
Yes.
You are having variables which can take only discrete factors. Okay, that is fine. The one advantage of design of experiments is if you are doing factors at -1, and all that, it is essentially meant for only those settings. It very strictly states that you cannot interpolate between the settings. You cannot interpolate between the settings. That is why when you have temperature, pressure, you can also consider catalyst as a factor. Catalyst anyway is not like temperature and pressure because it is not quantitative, it is qualitative. So, but what you are doing is like you are coding your variables for temperature as -1 and +1. Similarly, you are coding for pressure as -1 and +1. Catalyst also you can code as catalyst -1 can be a low grade catalyst and catalyst +1 can be a high grade catalyst. So this is a fixed effect model where your model is only applicable not only within the range of your data points, but also at the fixed values of the data points. So I haven't worked with the Boolean gates and discrete mathematics before, but what I would imagine is cautiously I would say that you can even extend this design of experiments to your discrete variables, and by suitable, and I told you how to do the coding. The coding will be done by actual value minus average value divided by maximum value minus average value. So that is the coding formula. If you do it in a coding formula, you consistently will get -1 and +1 for all your discrete elements. And I still believe you can do the mathematical model development on these fronts. So the regression will tell you what are the weights of the mathematical model. But now, when you are going to do the optimization, you will have to be very careful. None of the conventional continuous optimization methods will work in this case. You have to go for a discrete optimization algorithm.
Okay. And sir, what about the transformation? When I will come to know about whether the transformation is required or not?
Okay. If the values are very, very far apart and they are different from each other, for example, time may be, as I said, in seconds, maybe 10 seconds to 60 seconds, whereas temperature may be 800 degrees centigrade to 1000 degrees centigrade. So when you have this large discrepancy between your individual factors, for example, pH may be from 2 to 10, whereas your initial concentration can be from 100 to 500. So each factor is having different orders of magnitude. What you can do is each factor you arrest it between -1 and 1, or 0 and 1. This kind of scaling if you do, and the scaling formula is the same. For each value, you find the average value, you know the maximum value and the minimum value. So actual value minus minimum value divided by average value minus minimum value. If you do, then all the variables will be coded between -1 and +1, and then you can carry out the regression analysis. So it depends on your variables, what units they have and what magnitudes they have. And when you code it also, all the equations x1, x2, x3 are becoming independent of units. Okay, so your response will not be, for example, I don't know what would be the response. For example, your response is meters per second, beta naught plus beta 1 x1, and then you have beta 2 x2. x1 and x2 are different units. Then beta 1 and beta 2 will have different units, so that ultimately they give the same units as meters per second, the response. So there will be a lot of confusion in the unit conversion and the units for beta 1 and beta 2. But if you code the variables, as I told you, x1 and x2 will be unitless or dimensionless, and then your beta 1 and beta 2 will also be dimensionless. They will not be dimensionless. The x1 and x2 will be dimensionless, but beta 1 and beta 2 will have the same dimensions as that of the response. And by looking at which beta 1 is having a higher value and which beta 2 is lower than beta 1, then you can say that beta 1 is having or x1 is having more influence on the process. So that is a big advantage of coding.
Any other question from participant sides before Professor Kannan leave the session? Yeah, but voice is very low. You can type your question. I can ask on behalf of you.
Sir, I have a question.
Yes, yes, we can hear you now.
No, sir.
Yeah, you can go ahead. Yes, yes.
Yes, sir. Sir, I have a question. Suppose I have created a mathematical model with the experimental design. Suppose I use 30 or any number of cost. Now I want to validate that mathematical model. What value you should suggest?
Yeah, very good question. See, there are two things. One is validation of your model. See, normally what we do is you have already done your experiments, you have done repeats hopefully, and then you have developed a mathematical model. So normally, even though this model I told you is for fixed effects, okay, let us assume that all the independent factors or variables in your model are quantitative. Is it all of the, are you having categorical
Yes,
variables?
sir. I have all quantitative model, and I have 4 input parameter. I have 4 input parameter and 4 quantitative model
Okay.
variables. Sorry.
That's fine. So in such a case, what you must do is, as I have done, you have to do something called as validation experiment. Okay, you have already done the experiment, you have got the values, and it is fitting with the R squared of 0.99, whatever. Okay, right. There are several ways of answering your question. So I'm just pausing for a second. See, there is something, if you look at my PowerPoint slides, because of lack of time, I did not do something called as lack of fit. But if you go through my PowerPoint, there is something called as lack of fit. And if your model is having, insignificant lack of fit, then your model is good enough. So that is more difficult to understand. What you do is there is something called as adjusted R squared. So what you can do is you can develop with a simple model, find the R squared value and the adjusted R squared value. adjusted R squared, let us say the R squared value is 0.9 and adjusted R squared value is 0.85. Then you add more terms in your model. And when you add more terms in your model, the adjusted R squared will shoot up to 0.95. And if the R squared is shooting up to 0.95 and adjusted R squared is also increasing to 0.93, you are on the right track. Your model is hungry for more terms. Then what you do is you add some more terms. R squared may become 0.99, but adjusted R squared, which had improved to 0.93, will now may become 0.85 or 0.87. So this is a warning that you have added too many parameters in your model. If you have added too many parameters in your model, R squared will keep increasing. And when the number of model parameters is equal to your number of data points, you are not doing regression, you are doing only equation solving. And you will be able to get a R squared of 1, where all the response values will match with all your experimental values. But that is only equation solving. But the adjusted R squared may be as low as 0.8 or 0.75. So what you do is you keep adding more and more terms to your model and see where the adjusted R squared passes through a maximum. And there you stop adding model parameters.
Okay, sir. Thank you, sir.
Okay, I think Dr. Aryan has temporarily disconnected. So I guess we can wait for him.
Any other questions from participant side? Yeah, I got disconnected actually. So any other questions from participant side? Hello? Any other questions from participant side before we will close the session?
I think Siddharth has, or Rajvinder Kaur, I think has, somebody has lifted the hand.
Okay.
I think Rajvinder Kaur, perhaps.
Any question from participant sides? They can ask the before we will end this session actually.
Okay, Syed, three-factor factorial effects model is also one way we can do modeling. Three-factor instead of two-factor design. Syed Saim Ali has asked one question. Sir,
Yes,
three-factor factorial model. Yeah, it's also one way of doing the modeling. So rather than if you want to not do with the two levels, one upper level and one lower level, there are also methodologies available for three-factor design, where instead of having 2 power n, you have 3 power n, where 3 is the number of levels and n is the number of variables. So you end up doing more experiments, but again, using the analysis of variance and the sum of squares, degrees of freedom, p-value, everything you can do exactly the same way and you can get your conclusions. It's just that your experimental design is such that you need to investigate at 3 levels rather than at 2 levels.
Any other questions? So I think there are no more questions. So I would say thank you very much for Professor Kannan to accept our invitations to be the part of this course as a very short notice actually. And he has very well presented this response circular statics analysis of experiments. So thank you very much, sir, to be the part of this course and all these participants. And we will have next session at 1 o'clock on molecular modeling and computation analysis by Dr. Gaurav Manik from IIT Roorkee. So we will close this session here, sir. Thank you very much, sir, once again.
You're welcome. Bye.
Yeah, bye.